Let us solve this given non-homogeneous higher order equation, but now we're going to use the variation parameter, specifically the use of Wronskian of functions. Now we can of course solve this using the previously discussed method, following the trial particular solution, the given table, because this g of x is also, or can also be found there, but we are going to use this method just to differentiate the Wronskian of functions strategy, because this may there might be some equations which cannot be solved by the particular solution. Nevertheless, this is still y sub c plus y sub p. Now y sub c, as we know, is as to be the complementary solution when this g of x is of course equal to 0. So we are going to assume a homogeneous equation following this, coming up with a auxiliary equation, solve the auxiliary equation, and provide the appropriate y sub c. Now for y sub p, as mentioned, we will not be using the particular solution of the table presented in the previous videos, but we are going to use here this process here, and I have placed already some of the formulas to save some time, because this video will really need a lot of space and time in the discussion of this. At the same time, since we are going to talk about Wronskian functions, we need to be reminded of the examples or the previous videos pertaining to the solution of the Wronskian. So let's start first. Before we start, take note that as part of the solution involved in y sub c, it can be expressed in this form, where y sub 1 and y sub 2 might be emphasized because they are also needed for our y sub b solution. Okay, because we also have y sub 1 and y sub 2 here, and that because we don't know how many terms would be there. Of course, aside from that, there is a u sub 1 and u sub 2 which can be gathered or generated from these solutions, where w is the Wronskian. Let's have it later. So let's start with the y sub c process. Of course, f of dy equal to 0, we will have here d squared minus 4d plus 4 times y equal to 0. Okay, so our auxiliary equation is m squared minus 4m plus 4 equal to 0. Solving for the roots, we can factor this m minus 2, please review the factoring, and with that, our first root is positive 2, which is also the value of our second root. Hence, we will be using the general solution for y sub c, where when our roots of the auxiliary equations are repeated and actually real. So this is our form. So you will have here e to the power of mx times c sub 1 plus c sub 2x. We end up on the second term because we only have multiplicity of 2 for our root of 2. With this, our y sub c is e to the power of 2x times c sub 1 plus c sub 2x. In the previous videos, we're able to accept this even without distributing e to the power of 2x. But let's try to distribute that, because our y sub c could give us again the y sub 2 and y sub 1, which are also important in our y sub b. So we will have here c sub 1 e to the power of 2x plus c sub 2x e to the power of 2x. Okay, with this is our y sub 1 and this is our y sub 2 as indicated in this process here. We will be using that for our y sub b later, but nevertheless, this is already acceptable as our y sub c, a portion of our solution. Okay, now for y sub p, we need the y sub 1 and y sub 2 indicated here, but aside from that, we need u sub 1 and u sub 2. They can be generated from this process, as u sub 1 is the integral of the u prime sub 1 and u sub 2 is the integral of u prime sub 2. But the u primes are also generated by the ratio of the Wronskian and w sub 1 and w sub 2. The Wronskian of this function, okay, we'll be using the functions y sub 1 and y sub 2. The Wronskian, e to the power of 2x, and x e to the power of 2x, is already identified in a specific video pertaining on the solution of Wronskian. I may not show that here because it will take us much time. I would like you, and I am encouraging you to view that video. The link is also posted below. in the comment portion, or in the what do you call this one, in the caption of this video, because I would like you to view that on your own. Here I'm just going to automatically give you the value of the Wronskian as already identified as e to the power of 4x. Okay, so the Wronskian is actually identified as the determinant of an equivalent matrix. The equivalent matrix, I'm also going to present it either way. So we'll have this matrix here following the functions e to the power of 2x and x e to the power of 2x. Actually, these were also presented in the video pertaining on the Wronskian, but I'm going to show it in a way here because this will be also used in solving w sub 1 and w sub 2. I'm just not going to share the process of solving the Wronskian e to the power of 4x. The second row would be the first derivatives of the first row. So you have e to the power of 2x times 2. And you have here, of course, in the previous video as well, we were able to identify this to be a product of two functions. So you will have x and then e to the power of 2x times 2 plus e to the power of 2x times the derivative of x, which is just equal to 1. So we will have this as our matrix in getting the Wronskian of e to the power of 4x, e to the power of 2x, x e to the power of 2x, twice e to the power of 2x, and then you have twice x e to the power of 2x plus e to the power of 2x. Again, this was used in solving the Wronskian. Please review that video on your own time. My point of presenting this again, because we can use that in solving w sub 1 and w sub 2. Okay? W sub 1 is a version of the matrix where the first column, the first entry, would be 0. And if there are entries in between, it will also be 0 until you reach the last entry. In this case, we only have 2 entries. Okay? We only have 2 entries here. And that will mean the last entry for that column having 0 as the first entry is this g of x here. Okay? This g of x. So x plus 1 times e to the power of 2x. So we have x plus 1 times e to the power of 2x. For our second column, we just simply use the same entries. X e to the power of 2x. And you have here twice x e to the power of 2x plus e to the power of 2x. Okay? For Wronskian 2, we will have this form on the second row. So you will have the second row 0 and x plus 1 e to the power of 2x. But the first row would be the original first row of the matrix involved in solving the Wronskian. So e to the power of 2x and twice e to the power of 2x. So we'll be solving them independently. So let's start with the w sub 1. Of course, with this, that's 0. Then, in this area, you'll have minus x plus 1 e to the power of 2x times x e to the power of 2x, which will generate a result of negative x times x plus 1 e to the power of 4x combining the exponents. Let's not simplify x times x plus 1 because we might be dealing with that problem later. For your second, this one here, so you have e to the power of 2x times x plus 1 e to the power of 2x, then minus this region, of course, that's equal to 0. So simplify the red portion, you will just have x plus 1 positive e to the power of 4x. This is our w sub 2, and this was our w sub 1. Okay, we will be using w, the Wronskian, w sub 1 and w sub 2 in solving for here, this formula. The u prime of 1 and u prime of 2, the ratio of both. Okay, so let's have that. U prime of 1 is w sub 1 over w. Okay, so u prime, our w sub 1 is this colored blue here, negative x plus 1 e to the power of 4x over your Wronskian e to the power of 4x. So that will be cancelled, meaning you will have negative x and then x plus 1. Again, let's not multiply them in the meantime. We might have some problems as we deal with them later. Okay, so with that, or yeah, you can multiply if you would like to. So you will have negative x squared minus x. Let's have that. U prime of 2 is the ratio of w2 and w. This is our w2. x plus 1 e to the power of 4x. Again, our w here, Wronskian, e to the power of 4x. So you'll have x plus 1. So take note of this too, because we will be using them. Here the formula going up. We are done with this. We will be getting the u sub 1 and u sub 2 to be paired with our y sub 1 and y sub 2 already identified earlier to get our y sub b. Okay? So I might be moving on the next page. Take note of this too. Okay? Let me have this next page. Okay? Our u prime of 1 is actually negative x squared minus x. I will be checking that later. U prime of 2 is x plus 1. Okay? So what we need to do, let me check again. Yeah, that's correct. Minus, minus, and then positive and positive. The next part here is to come up with our u sub 1. So simply take the integral of u prime sub 1. And of course, if you're going to take the, since this is the first derivative, we are expecting also addition of dx later, as this is our variable. So don't be confused why dx will appear later. It will be like this. The integral of your negative x squared minus x, and then you will add here dx so that you can integrate that. Okay, so you will have here negative of x squared dx minus x dx, and for u sub 1 is of course by integration you add exponents. You will have your negative x cubed over 3, or 1/3. Let's use 1/3. Sorry for that. Okay, we'll be having here negative 1/3 of x cubed, and then next you will have here negative 1/2 of x squared, and of course you can have here plus c. But let's not add c later. Let's add c because we will be combining it with our solution later on. That's u sub 1. Now for u sub 2 u sub 2 rather. U sub 2, this is the integral of u prime of 2. Again, you will d of x will appear here. So you have x plus 1 dx. So solve that. Integral of x dx plus integral of dx. So you have here 1/2. Okay, you will still have 1/2. Positive 1/2 x squared plus x, as this is the integral of dx here. But of course, again, no c in the meantime. So you have u sub 2, and then you have your u sub 1. Going back to the previous page, we need u sub 2 and u sub 1 to be paired with y sub 1 and y sub 2 indicated here. This is our y sub 1 and y sub 2. So let's integrate that on our solution. What that will be for our y sub b. So our y sub b must be u sub 1, y sub 1, plus u sub 2, y sub 2. We only have 2. So our u sub 1, here is our u sub 1, negative 1/3 of x cubed minus 1/2 of x squared times your y sub 1 earlier. Please take out this e to the power of 2x and x e to the power of 2x. So you have e to the power of 2x. Plus your u sub 2, 1/2 x squared plus x times x e to the power of 2x. So our y sub b, you'll have negative 1/3 x cubed e to the power of 2x. As you can see, it really has a lot of steps to be here. Then minus 1/2 x squared e to the power of 2x. Here plus 1/2 x squared this is x cubed. This is x cubed because you have another x here. X cubed e to the power of 2x, and then plus x squared e to the power of 2x. You can combine this x cubed to that. So you have 1/3 negative 1/3 plus 1/2 LCD. You will have positive 1/6. Take note of that because this is 2/6, and this is 3/6. So positive 1/6 x cubed e to the power of 2x, and you have here minus 1/2, and this is 1. So you have positive 1/2 x squared e to the power of 2x. As you can see, this is just our y sub b. Okay? So we really need a lot of steps. Now, to finalize our answers. Going back to the um, previous page. This is our solution just for this singular item. Y sub c plus y sub b. And this was our y sub c earlier. Let me erase these circles here, because I'm going to copy this for our y sub c. Copy that and move it on the other page. Because the solution of y, sorry for this, let me paste it here. Okay, this is our y sub c. If I'm correct, this is our y sub c. C sub 1. Okay. Because our y is y sub c plus y sub b. So simply combine them, you will have c sub 1 e to the power of 2x plus c sub 2 x e to the power of 2x. Then your y sub b plus 1 over 6 x cubed e to the power of 2x plus 1 half x squared e to the power of 2x. Or if you would like to rearrange these two so that you will have x squared first to arrange the exponents, you may, but since to pattern that to the previous solution, let's have that. So this is now the bottom line solution of all. This is when we are going to use this method for violation of parameters, specifically the Wronskian functions. As mentioned, this problem here may also be solved under the previously discussed methods using the y sub p table. But but for some which can't be solved under that, so this is now the start of a new method using the Wronskian functions. Thank you very much for watching.